So if nuclear spin quantum number I, if it is 0, then we can say that the nucleus is not spinning. Okay. Therefore, this nucleus is NMR inactive. Okay, the nuclei having nuclear spin quantum number 0 are NMR inactive. Okay, we are not going to bother about this. If I is not equal to 0, okay, the I value of a nucleus may be half or 1 by 2 or 3 by 2, 5 by 2, I is equal to 1, 2, 3, etc. If I is not equal to 0, then those nuclei have the property of spin. Then the spinning nucleus is active in the NMR. Okay, it is NMR. So only those nuclei whose I value is not equal to 0 are NMR active nuclei. Okay, and here observe carefully, this is very important. Here I said I not equal to 0. In this, two important things we have to focus upon. What is that? Number one, two important things. If I value equal to half, okay, if any isotope having a nuclear spin quantum number as half, then that nucleus, okay, that spinning nucleus, right, in which the positive charge is distributed uniformly and there is a spherical distribution of positive charge exists. Okay, so I is equal to half means spherical distribution of positive charge exists in the nucleus. So we can say that nucleus is perfectly spherical in shape. Okay, so here the nucleus is perfectly spherical. It carry positive charge and perfectly spherical. Right? If you take nucleus having I value greater than half, what is mean by that? If I is equal to 1, 3 by 2 or 2, 5 by 2, etc. In those nuclei, okay, this, when the nucleus spins, right, the spinning nucleus having I greater than half, right, it gives what is called the charge of the nucleus, right, it is not uniform, right. Actually, you'll get non-spherical, distribution of nuclear charge, positive charge exists in the nucleus. It is not spherical. We call these type of nucleus as quadrupole nucleus. Quadrupolar, okay, QUA, quadrupolar nucleus. Quadrupole nucleus or quadrupolar nucleus. Okay. Yes, these nuclei are also NMR active, but the study of NMR spectrum of these nuclei is little complicated due to the quadrupole interaction. Okay, what is quadrupole interaction? Right? Those things we'll discuss under NQR. I'm not going to discuss now, but keep this point in mind. So what we are going to do, so non-spherical means the positive charge may appear, okay, like this, or may appear like this, depending upon the nucleus. Okay. For this nuclei, the spherical nucleus is changed into or distorted into non-spherical. Okay. The measure of this deviation, okay, measure of the deviation of the nucleus positive charge from the spherical symmetry is what we call as quadrupole moment, which is denoted by the symbol Q. What is Q? Q is called nuclear quadrupole moment. Okay, nuclear. See, quadrupole means having four charges, right? Having four charges. What is meant by this? Let me show it in the next page. Take a look. So, nuclear quadrupole moment. Nuclear quadrupole moment is given by the symbol Q. Okay, Q into charge of the nucleus. Okay, this is actually average charge of the nucleus, and Q is the distortion, right? Now, for some nuclei, the Q value may be positive. For some other nuclei, the Q value may be negative. So, whether Q is positive or negative, that depends on the nucleus. Okay, suppose this product E into Q, if it is 0, it means there is no quadrupole moment. That nucleus is perfectly spherical. It's a spherical nucleus, right? Suppose if E into Q, called electric quadrupole moment, if E into Q, if it is greater than 0, what does this indicate? It indicates that along the spinning axis, this is spinning axis, along the spinning axis we have more charge distribution. Along the spinning axis we have more charge distribution, right? So I put plus here, minus here, plus here and minus here. So this plus indicates a pole, minus indicate another pole. So we have 4 poles, so it is a quadrupole. Okay, if E into Q is positive, greater than 0, we get a spherical charge distribution, or positive charge is distributed more along the spinning axis. This is actually spinning axis, and this shape is often called as prolate shape. This prolate. Suppose if E into Q, if it is less than 0, meaning negative. If E into Q is negative, then along the spinning axis the charge distribution is less, whereas perpendicular to that the charge distribution is more. Okay, so I'll put 4 charges. These are all poles, so we have 4 poles. It is called quadrupole. Okay, we call this as oblate symmetry, right? So for oblate symmetry, symmetric distribution of nucleus charge, or oblate symmetry of the nucleus, E into Q is less than 0, meaning negative. Right? Listen, E is always positive. In this case, E is always positive. So the sign is actually determined by capital Q. If capital Q is positive, it is prolate symmetric nucleus. If the Q value is negative, then it is oblate nucleus. Right? The charge is distributed in this manner. Okay. Listen, most nucleus having I greater than half, right? Most nuclei having I value greater than half, they have Q value positive. Quadrupole moment is, nuclear quadrupole moment is positive. So most nuclei shows prolate symmetry in the nuclear charge distribution. But some nuclei having I greater than half have Q value negative. Examples include chlorine 35, chlorine 37, iodine 127, copper 63, copper 65. Okay, then nitrogen N15. Okay, for these nuclei, I value, right? The nuclear quadrupole moment value is negative. Right? Chlorine 35, chlorine 37, iodine 127, copper 63, copper 65, right? Lithium 7. These are a few examples for nuclei for which Q is negative. For these isotopes, the nuclear charge appears as oblate symmetric. Okay, it is oblate symmetric nucleus. Right? Listen, these nuclei are also NMR active, no doubt in that. But the NMR spectrum of these nuclei, right, is very difficult or complex to study due to this quadrupole interactions. Right? What is quadrupole interaction? We'll discuss that under NQR. But because of this quadrupole nucleus, okay, some other effects happen, and because of that, the NMR spectrum become complex. Right? So we are not going to in this NMR basics of NMR course. I am not going to discuss about nuclei having I greater than half. I am going to focus only on nuclei having I is equal to half. Right? For I equal to half nucleus, the nucleus is perfectly spherical. Right? Then, so I have told you we are going to discuss only about I is equal to half nuclei. We are going to focus only on I equal to half nuclei. We are not going to study other nuclei. Right? And listen, for I is equal to half, then the nucleus have the property of spin. Okay? Nucleus has the property of spin. Right? Because I is not 0, I is equal to half, so it has the property of spin. Right? Just for understanding purpose, I will draw like this. Suppose this is a nucleus. The nucleus is spinning about its own axis. Right? And remember, this is something like rotational motion, right, or a spinning motion. This spinning motion is associated with an angular momentum. Okay, in quantum mechanically, right, people have found that nuclei, right, every nucleus has an angular momentum, intrinsic angular momentum, right. It's called spin, right, intrinsic property called spin. That spin is associated with the angular momentum. Right, and this angular momentum is called nucleus or nuclear spin angular momentum. So let me write here, nuclear spin angular momentum, which is denoted as P. And remember, nuclear spin angular momentum is a vector. It has direction and magnitude. Okay, and what are the allowed values? Listen carefully. This is actually a subatomic particle, right? This microscopic particle. For microscopic particles, angular momentum values are quantized. Angular momentum is quantized, right? So right here, spin angular momentum is quantized. Meaning, it takes only certain allowed values, right? What is the magnitude of spin angular momentum? Is it magnitude of spin angular momentum? We often represent this as P. Observe carefully. If I write simply P, it means we are talking about the magnitude of the angular momentum, right? Listen, quantum mechanically, this angular momentum is equal to h cross into square root of I into I plus 1. Right? This is the formula for nuclear spin angular momentum is equal to h cross into square root of I into I plus 1, where I is the nuclear spin quantum number and h cross, you know very well, h cross is nothing but h by 2. Planck constant by 2 pi, right? And I can take value 0, half, 1, 3 by 2, etc. etc. Right? I value cannot be negative, but I takes different values, right? Like I takes values like 0, but I0 means it is inactive nucleus. We are not going to discuss that. I can be half, I can be 1, I can be 3 by 2, I can be 2, etc. etc. Okay. Listen, if I put I is equal to 0 here, I will get an angular momentum of 0. If I put I equal to 0. If I put I is equal to, for example, if I put I is equal to half here, half into half plus 1 is 3 by 2. So we will get square root of 3 by 4. So we get h cross into square root of 3 by 4. 3 by 4. This is an extra allowed value. Then if I put I is equal to 1, 1 into 1 plus 1, I will get square root of 2. So h cross into square root of 2. Right? If I put 3 by 2 here, 3 by 2 into 3 by 2 plus 1 is 5 by 2. So 5 into 3, 15. Square root of 15 by 4 we get. So these are all the allowed values of spin angular momentum of nucleus. Okay. Nucleus can take only these allowed values. See, between, see what is the root 2? Root 2 is, okay, let me take this square root of 3 by 4. Square root of 3 by 4 is somewhat roughly say 0.7 or 0.6. Okay, 0.6 h cross. And this is 1.414 h cross. Between 0.6 and 1.4, we can see many values, 0.8 to 0.9, 1.1, 1.2. So many values are there. But angular momentum takes only this value, then the next value is this. Then the next value is this. Only these values are allowed for angular momentum. Angular momentum is quantized for the nucleus because nucleus is a microscopic object. Okay, for any microscopic object, you know very well, angular momentum is usually quantized. Okay, so nuclear spin angular momentum is quantized. Okay, and the magnitude of nuclear spin quantum angular momentum can be obtained by using this formula, where I is nothing but nuclear spin quantum number. Okay, said angular momentum is quantized. For different nucleus, we have different magnitude of angular momentum. Now, when you keep the nucleus in a magnetic field, what will happen? Right? Suppose I'll take a magnetic field like this. Say this is North Pole, this is South Pole. Okay. Now, assume that I have this is the direction of the magnetic force, magnetic line of force. Just for understanding purpose, I am drawing like this. Okay, this is the axis. Now I have a nucleus here. I have a nucleus here. Listen carefully. This nucleus has the angular momentum, right? Spin angular momentum. Okay, the spin angular momentum in the presence of magnetic field. When the magnetic field, I am applying some magnetic field. Right? When you apply a magnetic field, the angular momentum, right, orient in a different direction. They orient in a different direction in space. Okay, so this is the spinning nucleus. It has angular momentum. The angular momentum can orient in this way. Listen, on paper it is easy to show like this, but actually speaking, see, it makes some angle with the spinning axis or the external field axis. Okay? This is the external magnetic field axis, right? With respect to that axis, the spinning nucleus, the angular momentum of the spinning nucleus makes some angle theta. Remember that theta is also quantized. This theta is also quantized. Okay. And listen carefully. Just for our convenience, I have shown this angular momentum in this direction. But it can be anywhere around this axis, correct? Around this magnetic external magnetic field axis, right? This angular momentum vector can be anywhere around this axis. So, since it can be anywhere, I can draw a cone here. I can draw a cone here. So, along this cone, the angular momentum can be present anywhere. Okay. So listen carefully. Angular momentum is quantized, right? In the presence of external magnetic field, the angular momentum orients in a definite direction in space, right? And in this case, listen, the angular momentum, right, orients in this direction. It can also take another orientation. Let me show you here. For spin half nucleus, if I is equal to half, there are two possible orientations. This is one possible orientation. The other orientation, let me show here. The other possible orientation, this is the axis of the magnetic field, right? The other orientation is it can orient in this direction. The angular momentum can be in this direction, which makes an angle theta, and this theta from this axis and this theta from this axis, they are one and the same. Okay, from this direction it is theta, from this direction is theta. These two thetas are one and the same. And listen carefully, this angular momentum can also present anywhere along this cone, right? Let me draw a cone here, and this angular momentum can be anywhere in this cone. So here, see, this is the direction of the applied field. In this case, the angular momentum is in the direction of the applied field, whereas in this orientation, the angular momentum is opposite to the external magnetic field. Okay. Let me represent the external magnetic field as V naught. I'll represent this as V naught. Okay, but I'm going to show that since it is applied in the Z axis, so it is nothing but Vz. Okay, right. Now listen, spin half nucleus takes two possible orientations, right, in the presence of external magnetic field. The spin angular momentum, nucleus spin angular momentum takes two possible orientations. One aligned with the field, the other one is the opposing the field, right? And listen, it does not rotate. See carefully. It does not rotate actually. The angular momentum can be anywhere along this cone. Right? But later I am going to show that, I am going to tell you that there is a magnetic moment. The magnetic moment starts to spin, right, about this axis. Because of that, the angular momentum, this angular momentum also starts to spin. So now listen, we are going to discuss magnetic moment a little later, but till that, keep this in mind. Here, this angular momentum is not spinning, it is not rotating. Angular momentum can, what I am saying here, angular momentum can be anywhere on the surface of this cone. Okay, see, the axis is actually at the center of the cone, right? This angular momentum can be anywhere, right, on the surface of the cone, which makes a constant angle theta. Okay, so this is one orientation and this is another orientation. So for I equal to half nucleus, two orientations are possible. Okay, quantum mechanically we can show that for a nucleus having spin equal to I, there are 2I plus 1 orientations possible. Orientations of angular momentum possible. Okay, these orientations, right, are also represented by a quantum number called magnetic quantum number, right? So observe carefully, this is important. So for a nucleus having I spin I, there are 2I plus orientations possible. Therefore, for I is equal to half nucleus, we get two orientations, right? 2I plus 1. If I put I is equal to half here, I is equal to half here, I get 2. So there are two orientations possible. That's what I shown here. That's what I have shown here. Right? For I is equal to 1 nucleus, 2I plus 1, we get 3 orientations. Right? for I is equal to 2 nucleus, we get 5 orientations. So depending upon the I value, many orientations are possible. Repeat. Listen. For I is equal to half nucleus, okay, 2 orientations are possible. One aligned with the field, the other one is opposing the field. Okay, this is the angular momentum. Now draw a perpendicular to the z axis, and this magnitude is nothing but z component of the angular momentum. Okay, so I have positive z component and I have negative z component, because I is equal to half nucleus has 2 orientations, right? And the value of the z component of angular momentum is given by this formula mi into h cross, right? And z component of angular momentum also quantized. It takes only certain allowed values, okay, given by the formula mi into h cross, right? Take note. Right? What are the allowed values of the z component of angular momentum? Observe carefully. Z component of angular momentum is given by the formula mi into h cross, where mi is the magnetic quantum number, right? What are the allowed values of mi? Mi value depends on the value of I. Okay. For any nucleus having I, spin I, what are the allowed values for m possible? Minus I, okay, 2 plus I.
Plus I.
Yes. It takes values from minus I to plus I. Right? If you calculate, you will get 2i plus 1 total number. So, mi is the total number of mi values. Total number of mi values for a given value of I is equal to 2i plus 1. Okay, so each mi value gives you one particular orientation. Right? And these are all quantum numbers. They are just numbers. Alright. For example, for I is equal to half nucleus, okay, what are the allowed values of MIC? Mi can be minus half, then add 1 to this, add 1, yeah, minus half, then if you add plus 1, I'll get plus half. Okay, so the Mi values goes with the 1 increment, right? 1 increment. So these are the 2 allowed values of Mi. Okay, for each allowed value, you will get a particular orientation, right? Actually, listen, this is the magnetic field, external magnetic field axis, say Z axis, and we have the nucleus here. It has an angular momentum. This is total angular momentum, and this is the Z component of the angular momentum, right? And Z component of the angular momentum Pz is given as, right? Listen, for angular momentum which is aligned with the field, okay, which is in the same direction of the field, right, has Mi value plus half. Okay, so put Mi value plus half, you will get plus half, right here, Pz equal to plus half into h cross. Yes, this is the value of the Z component of angular momentum for I is equal to half nucleus. Right? What about the other possible value? Yes, the angular momentum can also be oriented in the opposite direction, which is opposite to the external magnetic field. Right? For this, Mi value should be minus half. Remember, for any orientation aligned with the field, we give positive number for Mi. For any orientation opposing the field, we give minus value for the Mi. So Mi plus half for this orientation, and Mi minus half should be given for this orientation because it is opposing the field. Okay, and what is the magnitude of the angular momentum? The magnitude of the angular momentum is minus half into h cross. I will get minus half into h cross. So this is the angular momentum, Z component of angular momentum for the orientation in which the angular momentum opposing the magnetic field strength. Okay. So for a spinning nucleus, there is a total spin angular momentum, and there is an Z component of angular momentum. Okay, this is very important. Keep this in mind. P is given by the formula P is equal to h cross into square root of I into I plus 1. Remember this formula. And Z component of angular momentum is given as h cross into Mi. Mi into h cross or h cross into Mi. right? Yes. So this is about the spin angular momentum of the nucleus, right? For I is equal to 1 nucleus, okay, what are the allowed values of Mi? Mi can take value -1. Okay, if I is equal to 1, start from -1, then add +1, 0, add +1, we get 1. So we get 3 possible values of Mi, which indicates that there are 3 possible orientations. 3 orientations are allowed. What are the 3 orientations? Let me show here. So this is the Z axis or magnetic field axis. Okay, and I have a nucleus here, and it has angular momentum, right? It has angular momentum aligned with the field, right? P. Then it has a component of angular momentum. Then another angular momentum, it is exactly in this direction, right? And another angular momentum is opposing the field. It has 3 orientations, right? See, this angular momentum can be anywhere along this cone. This angular momentum, this orientation in which the angular momentum can be anywhere on the surface of the cone. And another orientation is this. In this orientation, you draw a circle, and listen, this angular momentum can be anywhere on the surface of the circle. Then we have one more orientation. This orientation can be anywhere on the surface of the cone, which is in the downward side. Okay, it is upward cone and it's a downward cone. So on the surface of this downward cone, the angular momentum can present anywhere. Okay, and what are the allowed values of the angular momentum? You know very well, P is equal to, what is the allowed value? H cross into square root of I into I plus 1, this is the formula. So if I put I is equal to 1 here, I will get 1 into 1 plus 1 root of 2. So I will get H cross into root 2 or 1.414 into H cross. 1.414 into H cross. This is the total angular momentum of I is equal to 1 nucleus. And it takes 3 orientations. What are the Z component of this angular momentum? Right? Listen, for the angular momentum which is aligned with the field, we give plus value. So this is Mi plus 1 here. And for the angular momentum which is opposing the field, we give minus value, Mi equal to -1 for this. And the angular momentum which is exactly at the middle, right, will give the value as 0. Right. So for the aligned orientation, aligned with the field, right? Aligned orientation means aligned with the field. Aligned with the field. That's the meaning. For the aligned orientation, right, the Z component of angular momentum is equal to, the formula is Mi into H cross. Mi value is 1, so I'll get H cross. Right? For opposed orientation, meaning it is opposing the external field. For opposed orientation, Pz equal to, formula is Mi into H cross. For the opposed orientation, Mi is -1, so you'll get minus H cross. Right? And for the circular orientation, at the middle, right? For the circular orientation, meaning this orientation is at the middle. For the circular orientation, right? Pz equal to, I'm just using the word circular, right? Because this orientation appears like in this angle. In this orientation, we get a circular like shape, and the angular momentum can present anywhere on the surface of this. And for this, Pz equal to Mi into H cross. Mi value is 0, so we get 0. So these are the allowed values of the Z component of angular momentum. Remember, Z component of angular momentum are also quantized. I is equal to 1 nucleus can take only these 3 angular momentum, plus H cross, minus H cross, and 0. Right? Is this?
P.
See, I have told you this angle, the angle between the magnetic, the angular momentum and the Z axis, this angle is quantized. How to find this angle? Listen. So this is opposite side, and here I have 90 degree. So this is a hypotenuse. Okay, and this side is adjacent. So this is adjacent side. Yes. For adjacent side, we know the value half into h cross, and for the hypotenuse, the value is p, capital P. For I is equal to half nucleus, right? Capital P value is P value equal to, for I is equal to half. Put half here and half here. Half plus 1 is 3 by 2. So we get h cross into square root of 3 by 4. This is the value of P. For hypotenuse, the value is h cross by 3 by 4. And for the adjacent side, we have half into h cross. So the angle which is connecting the adjacent side and hypotenuse is cos theta. Okay. So what is cos theta? Cos theta is equal to opposite side, adjacent by hypotenuse. Adjacent is half into h cross, that is mi. Mi into h cross, we write the formula first. Okay, the z component of angular momentum, mi into h cross, divided by total angular momentum, which is h cross into square root of I into I plus 1. Let me write the formula first. Then h cross cancel. So this formula cos theta equal to mi by square root of I into I plus 1 will give you the value of cos theta. Right, and from this we can find the value of theta. That theta is a definite value, is a quantized value. Okay, for a given I value, for a given mi value, this theta is a quantized value. For this case, right here. So cos theta equal to, what's the value of mi? For the orientation aligned with the field, mi is plus of, and total angular momentum, right, is square root of 3 by 4. If I simplify this, you can find the value of theta. Okay, cos theta equal to 1 by 2 by square root of 3 by 4. If you make some simplification, you can find the value of theta. And remember, this theta is quantized. I is equal to half nucleus. For the mi plus half orientation, it takes this angle theta. Okay, we can find this angle just for time consumption. I didn't do that, but keep this in mind. We can get the value of theta by simplifying this. Okay, so this theta is also quantized. Keep this in mind. P is quantized, P is quantized, theta also quantized, and we can find the value of theta by making use of this formula. Right? T called spin magnetic moment. Spin magnetic moment, okay, which is denoted by the symbol mu. Since it is nuclear spin magnetic moment, I am using an extra additional quantity mu n. What is mu n? It is called the nuclear spin magnetic moment. Okay, listen carefully, this is very important. Why this magnetic moment arises? Is nucleus has magnetic moment? Yes, nucleus carry positive charge. It carry charge and it spins. Okay, for I is equal to, I not equal to 0 nuclei. Okay, the nucleus spin. Any spinning nucleus, right? I have told you, any spinning body has angular momentum. Okay, any spinning body carrying charge also produce magnetic moment. Yes, it also produce magnetic moment. Observe carefully, the magnetic moment and angular momentum, they are in the same direction for positively charged bodies. Okay, so P and mu are parallel to each other. P and mu are parallel to each other for most nuclei. Observe the word carefully. For most nuclei, P and mu are parallel to each other. Yes, there are exceptions available. Keep that in mind. For electron, suppose if we take electron carry negative charge. In the case of electron also spinning. It has angular momentum. It has angular momentum P. This electron angular momentum, and this spinning charge also creates a magnetic moment. That magnetic moment is opposite to this is electron magnetic moment. Electron magnetic moment is usually opposite to the spin angular momentum. This is the main difference between the nucleus and the electron. For many nuclei, not all, for many nuclei, right, the spin angular momentum and the magnetic moment both are orienting in the same direction. For electrons, the angular momentum and the magnetic moment, they orient in the opposite side. Okay, so what is the reason for getting the magnetic moment? It is because this body is not a neutral body. Okay, suppose I have some body which is neutral. If it is spinning, we get only angular momentum. But the spinning body carry charge. Any spinning charge creates magnetic moment. Okay, in which direction that magnetic moment vector exists, that depends upon the charge. If it is positive charge, yes, in most positive charge cases, P and mu are in the same direction. Okay, so this is very important. Keep this in mind. Now listen carefully. This mu, is also a vector. Like magnetic moment, angular momentum, spin angular momentum of the nucleus, magnetic moment is also a vector. Okay, and the magnitude of the vector, magnitude of the magnetic moment is usually denoted as mu. So I'll put mu n. Mu n means nuclear magnetic moment. Okay, so this is the magnitude. We represent magnitude as mu n. And listen carefully. The nuclear magnetic moment is directly proportional to the angular momentum of the nucleus. It is directly proportional to the angular momentum of the nucleus. Nucleus having larger angular momentum has larger magnetic moment. It depends. Okay, generally we can say like that. Generally, if nucleus having larger value of angular momentum, spin angular momentum, then the magnetic moment also large. If I equate this, we should put a quantity that Gn is called nuclear G factor into charge E by 2 into mass of the nucleus, right? This is the proportionality constant into P. This is the proportionality constant actually, and this proportionality constant is in carefully mu n equal to, I put this is Gn into E by 2m. Okay, we know very well the magnitude of angular momentum is h cross into square root of I into I plus 1. We know this, and in this E into h cross by 2m, right, is called nuclear Bohr magneton. Okay, let me write here E into h cross by 2m, right? It is represented as beta n. What is beta n? It is called nuclear Bohr magneton, and the value of nuclear Bohr magneton is 5.05. I'm sorry, 5.05 into 10 to the power minus 27 joule per Tesla. 5.05 10 to the power minus 27 joule per Tesla. That's the value of nuclear Bohr magneton. What is this? It's called nuclear Bohr magneton. Nuclear Bohr magneton. So I'll replace this by beta. So we get mu n, nuclear magnetic moment, is equal to Gn into beta n into square root of I into I plus 1. Okay, what is Gn? Gn is called nuclear G factor. What is nuclear G factor? Yes, we'll discuss that. And listen carefully. What is the importance of this formula? We get magnetic moment. Okay, and if you measure the magnitude of the nuclear magnetic moment is also quantized. See, Gn, beta n, these are all constant for a given nucleus. I repeat, for a given nucleus, Gn is constant, beta n is constant. And listen, depending upon the value of I, mu n value will change. And you know very well, I can take only certain allowed value, 0, half, 1, 3 by 2, correct? So since I values are quantized, I values are definite values, Okay, I can take only certain allowed values. Therefore, mu n also allowed. Mu1 also takes allowed value, which means mu1 is also quantized. Mu1 is also quantized. Is this clear to all? Listen, this quantity Gn into E by 2m is also called gyromagnetic ratio. So let me write here. Mu n is equal to this quantity. It is usually represented as gamma into P. What is gamma? This gamma is called gyromagnetic ratio. Gyromagnetic ratio. Yes, this is a very, very important quantity. We are going to discuss about this, okay, in the next session if possible, right? So, Gn into E by 2m, right? It is also called as gyromagnetic ratio, right? So, remember all these relations, right? All are very, very important. So, what is gyromagnetic ratio? Gyromagnetic ratio is nothing but mu n by P. If you know the magnitude of nuclear magnetic moment and the magnitude of spin angular momentum, yes, you can calculate gamma. Gamma is called gyromagnetic ratio.